Z2 symmetry is really called T parity because the T is negative. But we have to include an inert doublet. Okay, this can be a dark matter candidate. So once we have this symmetry, this term is forbidden. Okay. And this is complicated Higgs scalar potential, but basically no other effect for other coupling. So if you don't like this T parity, because sometimes people don't like the discrete symmetry, we can add something else, do something, and just add some high multiplet, okay, under the SU2. Okay, so basically you just replace this triplet with this one, and if it n larger than 3, then there's no this coupling. But we still need this term. Before I present the model, let me give a general discussion. There are basically only 3 possible new renormalizable Yukawa interaction involving the standard fragment with non-standard Higgs scalar. Okay. Of course, this is assumption based on colorless scalar. So if you have a scalar left required, then will be more complicated. And this is only 3. One is already mentioned Z model was a singlet. Another one was a doublet charge singlet, and this is a triplet. Okay, it's already Z model, Z Babu model, and type 2 Z. So if we want to forbid the AL coupling, okay, we can do that just like simply add this high multiplet under the SU2 sector. Okay. Here,
can I go back? So your high charge is really at the previous page.
This is the original model.
I think the page you were.
This one.
So the high charge is to forbid. Is this box here?
Yeah, this is naturally forbid these terms, but this is we have to propose. If once you have triplet, it will couple here. But this one you don't need to introduce anything. You just forbid these terms.
I couldn't figure out the gist of this high charge.
This is a high multiplet, like I will mention.
Okay, you can come back to this later.
Yeah. So basically, you replace this singlet and triplet by this. Okay, this is n large 3, can be 4, 5, 6, 7. Okay, under SU2, and this is the same Hubble charge. But then we can there's no coupling because for SU2 for the LL basically either one singlet or triplet. But if you have this high multiplet, you cannot form a singlet. Anyway, once we have this high representation multiplet, we'll end up to have a multi-high charge scalars. For example, for n equal to 5, we'll have like a triplet charges, doublet charges, okay, many charge scalars. The reason actually we propose this model was actually motivated by the LHC. This is a Higgs to photon excess, which is originally excesses solved by both CMS and Atlas, and currently only Atlas see something. Okay. So once you have a charge scalar, they will run in the loop. They will easily enhance the decay rate. I will come back this when I talk about phenomenology. Okay. And then we have here is the scalar potential. Okay. As I said, the most important is these terms for the exponential, other one is just normal terms. And notice since the even dimension one is due to the antisymmetric product, so there's no this kind of terms for even dimension multiplet. So we'll only end up odd dimension. So, and in this talk, our model is just purely concentrated for odd dimension multiplet, like 5, 7, etc. The constraint on this model, and so what we know, once you have high multiplet on SU2, they will have contribution to the row parameter if they have a VAF. Okay, so for example, if you have a doublet, this is a triplet one here, and this VAF has to be less than like a 4.4 GeV from row parameter. So for high multiplet, also around GeV. So it cannot be odd for the VAF. This is a very strong constraint on the model. In this model, we have two types of doublet charge. One is from triplet, one from the singlet. If you want the high multiplet, we'll have one from any multiplet will have a doublet charge, and this one, since we already keep the singlet there, we have these two. And this is a weak eigenstate basis. So we can diagonalize to have physical particle is called the mass eigenstates, P1 and P2. Okay, this is the mixing parameter now. The mass, the parameter in models here we have is kind of complicated, but this is once we write the mixing is simple. Okay, so this P is just a physical state.
Excuse me, do you have some Goldstone bosons not beaten?
Yeah, that's complicated. So we will make sure that it not happen. Yeah.
Okay.
So normally, if happen, you have to add something. Yeah. Yeah. So I want to emphasize that the P1, that's the lowest one. There are two doublet charge. One is lower mass, one is high mass. The lower one is well within the range of the LHC. The current LHC limit is around 200 to 400. I think depending on the development search. Also, I think this is a little bit model dependent. In our model, it's I think it's around 300 something.
So what is P1?
P1 is a doublet charge. The light doublet charge. There are two doublet charge particles. One is light one, another one heavy one. So we only concentrate the light one. The heavy one is too heavy to have any thing. Now let's talk about Majorana neutrinos. First is mass generation. In this model, the neutrino masses are generated radiatively at two loop level from this type of two loops. And this is the mass eigenstate of the doublet charge, and it's coupled with the doublet. Okay? And this two loop can be calculated easily. Okay? Although it's not that hard, and this is we have. And this is the mass of charge lepton, and the valve of the multiplet, and this is a mixing angle of the Wick's eigenstate, the mass eigenstate, the mixing angle of doublet charge. And this is a Chao couple, okay, for the singlet state coupled with the right-hand electron. And here, which we have here, and this is the matrix looks like. And the Yakar coupling basically constraint from lepton flavor physics. Okay, this is a constraint we have. Okay, and this is a matrix end up with this kind of a matrix. And this is the rule clearly tell us that the hierarchy is normal hierarchy. So this model predicts a normal hierarchy of the neutrino mass pattern. So if the experiment transform inverted hierarchy, this model will be wrong. Currently, it says preferred normal hierarchy. Who knows what happens in the future? Okay? Now let's talk about the neutrino-less double bit decay. And this is the tree diagram from short distance. This is a doubly charged mass ligand state coupled to the right-hand electron tree diagram. And this diagram is just the normal one from long distance contribution involving the neutrino mass terms. Okay. So you can calculate this too and put number in. You find out this is not much larger than this. Okay. This is not, of course, not surprising. This is neutrino from tulip level, and this is from tree level. Notice that there's no Majorana neutrino here, so anywhere here. Okay. So just this is just saying the black box is relevant in this theory. I want to just mention that our kind of theory has been also discussed by using kind of a effector operator approach. And this effector operator based on the right-handed left-down coupled with 2W. This is dimension 5 operator. He said the paper that is originally from this dimension 9 operator, which is left-hand number violin operator. Okay. And from this operator, and the neutrino mass is from this kind of loops, and this is can be even got another loop or more loops. If you have a 0 loop, and this is only 2. Okay. If you have one loop, it will be 3. And this is the mass element. And then the neutrino-less double bit decay. Okay. His conclusion, their conclusion, is same as ours. Normal hierarchy, and also the neutrino-less double bit can be large. Okay. That's a message in also in our paper. Now let me talk. Only 3. Let's talk about the phenomenology. Okay. And we have to thank to reach multi-charge scalars and make the phenomenology very rich. And which means first we have many physics from lepton flavor processes, such as the muoning, anti-muoning conversion, like effective EE to LL contact interactions, rare decay such as mu to 3E, and other like tau to 3 mu, 3E structures, and radiated flavor violating charge lepton decay, such as mu to gamma, like tau to mu gamma, etc. Okay. It's all due to the doublet Chao-Qiang scalar. And that's actually the constraint when we determine the mass matrix is basically all from the experimental value here. Okay. Also, we can search for doublet charge scalar at LHC. Okay. And so first, the fraction of doublet charge Higgs is basically from the WW fusion process, which is similar to the zero neutrino WK past the Chao-Qiang annihilation process. And this is actually the prediction. I don't see it is there here. My computer screen is here. I don't know why. Okay. So this is a production, and also the particle, the doublet charges also decay, and there are many channels. Okay? There's basically 6 channels, but 4 and 6 are not allowed in our models, and there's predictions of the decay rate, okay, in terms of the doublet charge mass. Okay. And this model, if n equal to 5, will have a triplet charge scalar decay. Typical diagrams is a triplet decay to 3W, which is the decay rate, and this triplet charge scalar also decay to 1W with the same sign that lepton. So this is the prediction for the decay rate in terms of the batch. Okay, we already put in the red represent this is 3W, blue is 1W2 dilepton. Okay, this is what's different set of parameters. I want to also emphasize that we have this is model has a same sign single dilepton signatures like this, and you can also look at the angular distribution for this cross sections. And to emphasize that in this model, the final state charge lepton are right-handed. So in principle, helicity measurement can be used to distinguish between all models and those whose doubly charged scalars couple only to the left-handed, like ALT, which is basically most people in the paper study is called type 2 seesaw. So that kind of theory. This theory is clearly different from their theory. If you look at the helicity, okay, so this is only right-handed. Also, this decay to dileptons was a lepton number violating, like E mu, E tau, and mu tau. This is our originally motivated us to studies. So this multi-charge Higgs contribution to the H to 2 photon and H to Z photon. As mentioned already, once you have charge scalars, it will have many additional loops contribution to the decay, such as this is multiply, okay, it's charge, and this is rate for H to 2 photon, also H to Z photons. And this is the predictions, okay, for N to the 5. Okay. For N to the 5, clearly the rate got enhanced. Okay. And easy to understand the other results on the previous CMS result too. Unfortunately, CMS now even smaller. Okay. So somehow, but this correlation, these two correlation of between the H to photon, H to Z photon, strongly depend on the charge representation, charge scalar or the marker. Okay, represent different, can either enhance or even suppress. Actually, this is one of the paper we is talking about the type 2 seesaw contribution. Sometimes can be enhanced, sometimes can suppressed. So sometimes support CMS, sometimes support others. Of course, with different set of parameters. Yeah. Okay, let me summarize this talk. So we proposed some models with multi-high charge scalars with an SU2 multiplet and a doublet charge SU2 singlet. Yes. Majorana neutrino masses are generated radially at tubular level with a normal neutrino mass hierarchy. The neutrinoless double-weighted decays can be sizable due to the tree exchanges process involving the doubly charged scalar, which is of course a short distance. Whereas the long-range contribution from Majorana neutrinos are negligible. And clearly, rich physics for electron flavor physics and unique signature at the LTC due to the multi-high charge scalars. Okay. Future data on the zero neutrino double decay as well as LT searches would distinguish our model from other neutrino models. Before the end of the session, I want to make some assessment that I'm going to organize this is called second international workshop on particle physics and cosmology of the Higgs and the Planck on October 8th to 11th. Fritsch, Professor Fritsch, actually, he will be here for 2 weeks in that period of time. And I chose this time is long weekend to celebrate the National Day due to this conference. Okay, thank you very much.
Okay, questions?
Are they constrained from STU
STU
parameters?
parameters, the contribution from multiplet. We did some calculations, not very much, yeah, because the mass is high, so not contribute.
What mass scale? Just from STU. Key parameter.
What do you mean, the mass? We use always, our parameter is all like more than 300 GeV for the doublet charging.
So then, but how about mass splitting?
Which mass is significant?
Okay, question. Mass scale and also the splitting in the multiplet.
We calculate sometime, I don't remember what we did not, since it's a contribution is not large, we did not present it in the papers.
Okay, any further questions?
Can the missing angles in the CP phase
No,
also be
we don't
predicted?
Is there
In
any
principle, yeah, in principle, could those numbers?
because Yaakawa company arbitrary.
Uh-huh.
Basically, they will have a phase there, can be large, depending on the experiment.
How about missing angles?
Mixed angle, also, we're not going to predict mixed angle. Mixed angle can be,
You said this earlier, but it would be nice if radiative Majorana mass generation can provide insight to why tri-bimaximal.
no, I don't want to provide, no, actually, I want to make a comment is most model predict this is, no hierarchy type of mixed angle, basically. But if you want to predict zero, like CT13, you need some symmetry. Since we don't have symmetry, we expect the mixed angle is just like the one we have as measured. So this is normal, natural, to have large mixed angle. So actually, small mixed angle, you need to put symmetry. For large, it's not, you don't have to put the symmetry there. We don't have any symmetry there.
You could have said that the model fully supports anarchy. So. Okay, any further questions?
No, I don't understand why people try to the CTS-13 already large, like 9 degree. People still, study proposed model symmetry. I don't understand. It's still predictably small, whatever. But it's not small. It's large. But if it's large, you don't need any symmetry. It's already there in the model. And people told me, oh, I predict this large. I said, every model predicts it large, unless you put symmetry to predict small.
I think for LHC, you didn't talk about production at all. Did you study it?
No, I talked
You
about
talked basically about decay.
no production. I talked about the first A production through just like the zero emission level decay, also from Chao-Qiang. I think Chao-Qiang got larger cross section.
Well,
But the thing that the figure cannot see it clearly here in this screen. This is, I got new the MacBook, so I don't know is this old or
Probably that's
it's
old.
not. It's not compatible. Anyway.
It's fair.
So the thing is, to get a benchmark, can LHC test? It goes back to you start with 300, 500 GeV.
No, I think that this model say on around 300 GeV.
No, I'm saying that it would be nice to have a benchmark whether LHC can do it at all. Given the mass balance.
Given the figures I have here, I think 500 is still okay at the next run at LHC.
What's the first section?
The section I think we have like.
Okay, it's too soft. I think
Anyway,
for experimentals, what we want to see is at what luminosity level with what signature does it look promising? Should we pay any attention at all? Basically,
Now, if you pay any attention on this is type 2 seesaw model, you should pay attention here.
anyway, that kind of study is more useful.
Yeah.
From my recollection of the right-handed neutrino search, things are not very promising.
Also, I don't understand why most people spend time working on type 2 seesaw. I think type 2 seesaw is perfect.
No, right. But the thing is, you have weak production. And then you talk about same sign dileptons and so on. Generic signatures like that, I think a right-hand neutrino is still a good benchmark.
Yeah.
It is not very promising.
Yeah. Also, this is a IoT search study was done 2007, long time ago.
Great. So you have.
But since 2007, I've been working on cosmology, dark matter, and
Maybe when
I should come back.
Maybe when Shuai runs at Tsinghua, you should give us an answer during experiment. Where's the benchmark? Okay. So, any further questions? Oh, okay. Great.
I noticed in your conclusion, in one of your models predict the normal hierarchy.
Yeah.
But maybe I missed it. If you can explain what
From the flavor constraint, we have a very special quark matrix. That matrix indicates normal hierarchy. That's constraint from experiment. Okay. Also, this is also supported by the effect operator guys. That paper also indicates this is normal hierarchy. You cannot get inverted hierarchy. Actually, most model, once you have a model, you will always predict normal hierarchy. It's not easy to predict the inverted hierarchy. Okay. Unless you put many junk to make it inverted.
Okay, I see no other questions. Let's thank the